Hi everyone, so in this video I'm going to be exploring some topics in organic chemistry. So I'll be talking about conformations of cyclohexane, and I will also be talking about SN1, SN2 and E1 and E2 reactions. So cyclohexane can take two conformations, a chair conformation and a boat conformation. The most stable conformation, however, is the chair, which is depicted by the diagram on the right. What makes it so stable is that steric hindrance is massively reduced. So orbital repulsion is also therefore reduced, which basically allows distribution of charge and more entropy and energetic stability within the molecule. So all carbon-carbon bonds then are staggered, and what that means is the four bonds around carbon are not aligned with each other on the carbon next door. So in a Newman projection, you will have a sort of staggered rather than eclipsed conformation on each carbon atom. The equatorial bonds are the blue bonds. Larger R groups prefer to take those positions because, again, they are less sterically hindered. They stick more out of the cyclohexane ring as opposed to the axial bonds in red. Note that the axial and equatorial bonds alternate on each carbon with their relative position above or below the plane of the cyclohexane ring. Cyclohexane flips between boat and chair more than 1,000 times per second. Now, in NMR, if you were to detect NMR, if you were to detect cyclohexane on NMR, you would get on a carbon NMR you'd detect one signal, and on a hydrogen NMR you'd detect one signal. The reason for that is and this is at higher temperatures, and I'll explain why. The reason for that is because the flips are so fast, you get a sort of a hybrid between axial and equatorial bonds, which essentially gives rise to one overall detection and one overall conformation. Whereas if you cool it down to up to say even like 60 Kelvin, what happens is you will get two sort of detections environments. You will get one for axial and one for equatorial. Even though they are technically on the same carbon, they share slightly different environments due to slightly different electronic interactions with that carbon due to relative positions and relative steric characteristics. So the reason that happens at low temperatures is because the flips are much slower, so the machine can detect it much more better. Basically, it has a high resolution. Well, the boat conformation is what the chair conformation goes into as it flips around. So this is the least stable because the hydrogens on the C1 and C4 positions are too close. There are 8 eclipsing hydrogens, the C2 and C3, and the C5 and C6. So that, again, even though they are only protons and are very relatively small, it still gives rise to instability in terms of steric hindrance. It also decreases the entropy of the molecule. The conformation, like I said before, the conformation does occur between the flipping of a boat. Always note that when the chair conformation goes from chair to boat to chair, all axial bonds become equatorial and all equatorial become axial. Like I mentioned before, at 298 Kelvin, there is only one peak on the HNMR, but at 220 Kelvin, there are two. Axial and equatorial hydrogens are much more distinguishable since flipping is slower. If we look at nucleophilic substitution, we have two types of nucleophilic substitution. If you just take a little read through this, I'm not actually going to read through this slide, but just have a little look. I'll give 30 seconds. Okay, so what essentially happens on an SN1 reaction is that a carbocation is produced. So how this works is the leaving group, as depicted by X, leaves first, which produces a carbocation, which is attacked um, by the nucleophile. The nucleophile attacks the sp2 hybridized orbital. In SN2, the nucleophile attacks the antibonding orbital of the CX bond, and dissociation occurs simultaneously, which leads to an inversion of configuration. If you have a little look at the solvents, SN1 prefer polar protic solvents, whereas SN2 prefer polar aprotic solvents. This is explained more. Pause the video and have a little look. It essentially works the same for elimination, E1 versus E2. Now, the difference is a nucleophile is a base that can attack a very delta positive carbon. Sometimes the base is too big to attack the delta positive carbon, so it has to attack further down the chain. What happens is it does lead to elimination. So if you take a base might attack a slightly delta positive proton. The proton, so it attacks the antibonding orbital of the carbon hydrogen bond. The proton dissociates, and you get a double bond formed, which then kicks off the leaving group. Now, as the in an E1, a carbocation does form first, which allows the base to attack the very delta positive hydrogen, whereas E2, the base attacks a slightly delta positive hydrogen, but both result in the formation of a carbon-carbon bond. In E1, the pi bond that forms is caused by the antibonding orbital of the carbon-hydrogen bond attacking the sp2 hybridized orbital of the carbocation, whereas in E2 the base attacks the antibonding orbital of the carbon alpha proton bond, and that antibonding orbital then attacks the antibonding orbital of the carbon leaving group bond. As you can see, there's a little bit about what sort of solvents they prefer and why. Let's just have a little read of that. And also, it's good to mention, like I've just mentioned before, in an E1 mechanism, the alpha hydrogen aligns with the p orbital of the carbocation. That's essentially to allow that antibonding, the carbon hydrogen antibonding orbital to attack the carbocation, the sp2 hybridized orbital, and in E2 the alpha hydrogen aligns with the antibonding orbital of the CX bond, again for the same reason.